Let's talk now about the finite difference schemes, and we will go through one particular partial differential equation, which is the advection equation. So this is the advection equation, and it is used usually to model transport phenomena or transport of substance in space. So X is actually called the spatial domain, and here it extends from A to B. T stands for the time. So U sub T is the time derivative of the concentration of some substance at time T, and X U sub X is the space derivative. So UTX is the concentration of some substance at time T for point X in space. And v is the velocity that the substance travels along the space domain X. So if the initial conditions, which means at time t is equal to 0, the solution is given at any point x in space is equal to fx, then the analytical solution is simply f of x plus v times t. So we will denote the approximate solution by the lowercase u, okay? Because the exact solution will be u capital letter. Okay. Now we will have to discretize the space x. We discretize it as follows. So we will use, for example, a uniform spatial step length of delta x. And as we said just now, the boundaries on the spatial domain are from A until B. So delta x is the distance between two consecutive space steps. So x0 here is the location of the first node. Of course, it is equal to A. And xn is the location of the last node, or the upper boundary. So A is the lower boundary and B is the upper boundary, x0 and xn. And xi is a location at the location of the ith node, okay, in the space domain. Okay. Now n is defined as the number of discretizations, okay, number of discretizations of the space domain. So A, we have A plus n times delta x should be equal to B. So delta x will be B minus A divided by n, okay? So if A is equal to 0 and B is equal to 1, and we are going to use let's say 10 discretizations, then delta x is equal to 1 minus 0 divided by 10, which means 0.1 is the space step length. Okay. Now if we choose, let's say, delta x is equal to 0.01, then we can calculate n as b minus a divided by delta x, and in this case will give me 1 minus 0 divided by 0.01, which means 100 steps. Okay. Now we will derive the finite difference scheme. So to derive the finite difference scheme, we will use the forward difference for time and the backward difference for the space derivatives. So u sub t, which is the time derivative of the concentration, will be substituted by ui n plus 1 minus ui n over delta t. So just pay attention here to this notation. So ui n plus 1. So basically what we mean here the I stands for the space node, and m plus 1 is the time that's in the future. So we have uim plus 1 minus uin over delta t. This will replace or approximate the time derivative. For the space derivative, we are going to use, as we said, the backward difference scheme. Okay, the backward difference scheme. So you have uin minus ui minus 1n over delta x is equal delta x. So v here, it is the velocity of the at which the concentration moves or along the space domain. So if you use these two approximation schemes and replace the original partial differential equation, that you take out the future solution, okay, the future solution at time n plus 1, and at point I, you leave it on the left side of the equation and you put everything on the right hand side of the equation, you get the FOU, or the final difference scheme to solve the PDE, okay, to solve the PDE. Okay, now this of course is an approximate solution. So since it is approximate solution, we will use the notation U, which is the lowercase, okay, the lowercase here. Now uin plus 1 is equal to uin minus v delta t over delta x times the difference uin minus ui minus 1n. Okay, so this is, as I said, is the FOU, or the first order upwind scheme. Now we can draw now a stencil, okay, the stencil. What is the stencil? Stencil is simply a graphical representation of the scheme, okay, the graphical representation of the approximate solution. So this is the space x, and this is the time t. So these are the discretizations. Okay, I minus 1, I, and I plus 1. So the distance between I minus 1, I is delta x, between I and I plus 1 is also delta x. So we have also here delta x. And the same thing goes for the time domain is discretized into substeps or time steps. Each time step has a length of delta t. So this will be the future. M plus 1 denotes the future solution, and N denotes the current solution. The current solution is, of course, is available, okay, is available to us. So what we are looking for is actually UI m plus 1, which is the solution at position I in the future. So will be this. We are looking for this. And the solution, which is on this time and space point, is dependent on the solution at the current time, and at the same point, in addition to the solution at the current time, but at the point just before the I, okay, just before the step I, which means a step I minus 1. Okay, so now that we have the approximate solution given by this equation, The actual implementation in a computer program is very simple. You will have one equation and you loop over all the time steps and the space steps. So the computation, now the problem is, if you want you want to calculate u0 at n plus 1, which is the future solution at this boundary, you will require u minus 1. It's very simple. So if you put I is equal to 0, you will need what? U minus 1. Okay, you will require u minus 1. Of course, which doesn't exist. This is the current solution at a point that is before the boundary, outside the boundary, or the lower boundary. Okay, outside the just before the lower boundary, it doesn't exist. So we have to pay attention to this, because we need to deal only with the computational nodes, that are bounded between the lower and upper boundary nodes. Okay, so these are called what? Computational boundary nodes. Okay, so now the solution is given to us at this point and at this point. So the computation nodes will be only those which are in between the boundaries. Okay, so basically u0n and unn are removed from the calculation of the finite difference scheme, and only their values are determined using the boundary conditions. So the boundary conditions should be given to us. So u0 at time n and u at n at the boundary, higher boundary, or the upper boundary n at time n are given from boundary conditions. Okay, now, so in the current example, of course, we'll assume that all these boundary conditions have 0 values. Okay, have 0 values. Now let's go now to assign some practical numerical values to the velocity and the initial conditions and boundary conditions. So we assume that the velocity is equal to 1, okay, and we assume that the solution at any point in space at time t is equal to 0. We are dealing here, of course, with the initial conditions, is equal to exponential minus 100 times x minus 0.4 squared. Okay, so this will be the position or the concentration at time t is equal to 0 at any point. So if you plot this, actually, if this is x, okay, and this is u, you get something like this. Okay, something like this. Now we will use also, we will need the boundary conditions. So the boundary conditions, we assume that a is equal to 0 and b is equal to 1. So this is the space. We have here the solution at any time is equal to 0, and the solution here at any time, or the concentration at any time, is equal to 0 as well. So this is at any time t, okay, 0 is equal to 0, and here the concentration at any time t at point B, which is 1, you can put here A, is equal to 0. Good. Next, we are going to use a space, a step length of 0.1. Okay, so we have delta x is equal to 0.1. So this means that n is equal to b minus a over delta x, which is equal to 1 minus 0 over 0.1. It gives me n is equal to 10. Okay, 10 spatial steps. Okay, now if we look at the space domain, we have from A, okay, so this is the lower boundary, until B, which is the upper boundary. Okay. Now the computational, the distance between each two consecutive space steps is 0.1. Now the computational nodes are these from U1 until U9. Okay, so we have to exclude the lower and upper boundary nodes. Okay. Now since V is equal to 1, delta T, we will choose delta T is equal to 0.05 seconds, and delta X, we have it equal to 0.1. We calculate the term V dt over dx is equal to 0.5. Now if you go back, if you recall the finite difference approximate solution is given by this equation. So we have this is equal to 0.5. Okay, we go here next. We get the finite difference scheme as follows. So the approximate concentration of some pollutant or substance at point I in the future, this means the future, is equal to the current concentration at the same point minus 0.5 times the difference between the concentrations at the current time between the current space node I and the concentration just at the node right before. So let's look now at this example where we selected V is equal to 1. We have V is equal to 1, so the advection equation becomes U sub t plus U sub x is equal to 0. Now assuming the initial condition as follows. So we have this concentration at time t is equal to 0, and at any position in space x is equal to exponential minus 100 times x minus 0.4 squared. Now if you plot this, so initially, so this is the solution, and at any time at time t is equal to 0 will be something like this. Starts here 0, then goes, it reaches to maximum 0.4, then it goes all the way to 0. So between 0 and 1 is something like this. So initially the concentration is high at 0.4, okay, and it gets lower at the left and right of the node number 4 or number 5. Now the boundary conditions we have here at any time when x is equal to 0 is equal to 0, and the concentration at any time when x is equal to 1 is also equal to 0. So the two boundaries, the concentration will be 0 at any time, not only at the initial time t is equal to 0. Now we are going to use 11 nodes, and this means that n is equal to what? 11 minus 1, it gives me 10, and we assume that the time step is 0.05 seconds. Okay. Now when n is equal to 10, this means that delta x is equal to b minus a divided by n, which means 1 minus 0 divided by 10. It gives me a space step length of 0.1. Okay, so the lower bound is u0, so this is a equal to 0. this is the lower bound, and the upper bound is b, so b is equal to 1, and this is the upper bound. And in this case, the computational nodes are from u1 until u9. These are all the computational nodes from x is equal to 0.1 and x is equal to 0.9. We will pre-calculate here the term v delta t divided by delta x is equal to 0.5, and in this case the finite difference scheme approximation becomes ui n plus 1 is equal to uin minus 0.5 uin minus uin minus uin minus 1n. Good. Now in the actual implementation, we have first always as a first step is to do some hand calculations, so just to get used to the notation. So first we calculate the initial values at all nodes. So we have here a is equal to 0, so here we have u0, and we have here, this is x of course, b is equal to 1, and this is u n, okay, u10. Now initially the solution is given as u0 at any node x is equal to exponential minus 100 x minus 0.4 squared. So what we have here, we will replace here x, we will replace x by u0, then u1, u2, all the way until u10. These are the computational nodes, of course, computational nodes. From the boundary conditions, we have the solution or the concentration at any time at the lower boundary is equal to 0, and at the upper boundary is also 0. So we do the hand calculations. So we have at the lower boundary 0, and at the upper boundary, which is un, is also equal to 0. So this is the upper boundary solution is given from boundary conditions. So this one given from boundary conditions. So we calculate the solution at the computational nodes. So here we just calculate u1, u2, u3 at time t is equal to 0. So we do the calculation, we substitute x every time here, so we have x, so we substitute one time by 0.1, we calculate, then we find it 0.0001. Then we put x is equal to 0.2 here, then we calculate u20. We substitute x is equal to 3 here in the equation, then we find 0.3679. Okay. Now if you put x is equal to 0.4, you find the maximum that is equal to 1, because 0.4 minus 0.5 gives you 0, exponential 0 gives you 1. That's the maximum. So as I said, we will have something like this. So at time t is equal to 0, you will have here 0, we have here 0, and in between at 0.1 you find something like this, 0.2 something like this, at 0.4 you have a maximum here, 1, so something like this, and it goes all the way to 0. This is the maximum. Good. Then this is at time t is equal to 0. Then we go for the next time step. The next time step, what we have, t is equal to 0.05 seconds. Okay, so this is t1. So what we do here, we have to come to this equation and we apply it. So we have the solution at when we put n is equal to 0, we get u1, okay? So u1, 1, so we have here I is equal to 1, here n is equal to 0. For I is equal to 1, what we have? u11. u11 is equal to u1n, which is 0, u10 minus, okay, so we have u10 minus 0.5 times the difference between the solution at the current node and the node just before. So if we do the math, you find 0.0001. Then for I is equal to 2, you do the same calculations, you find 0.0092. Then for I is equal to 3, you do the same calculation using the finite difference scheme, then you find 0.1931. Good? Now, of course, it becomes very tedious if you want to do it by hand for all the nodes and all times. Okay? So for this, we have to do, use computer code to simplify the calculations. And here I have flowchart for this. So we'll start first by initializing all the variables. Then we calculate x and the solution at time 0. Then we start incrementing. So we put n is equal to 0. Then we start the bigger loop. The bigger loop will loop over all time. Then we will loop over all the space steps. So let's start here by defining the variables. So we will define the variable n is equal to 10. This is the number of nodes minus 1. We have the lower boundary x min is equal to 0 and the upper boundary x max is equal to 1. So the boundaries are 0 and 1. This is a space boundary. We can calculate also here now delta x is equal to x max minus x min divided by n. So we get delta x. So delta x in this case it becomes what? 1 minus 0 divided by 10 gives 0.1. And we have delta t is equal to 0.05. Of course you can change the time step, but you have to be careful because of stability issues and convergence issues. The velocity we have at v is equal to 1 and the initial time value of t is 0. Okay. Then we calculate the constant v delta t over delta x. It will be equal to 0.5 as we calculated before. Okay. Then here we just create a vector. So this is just a vector. X here is equal to 0, 0.1 all the way until 1. So we need this vector later for the graphical representation of the solution. Okay. Now the initial conditions, what we have the solution at any time t is equal at time t is equal to 0 and at any position x is equal to exponential minus 100 times x minus 0.4 squared. We'll assign here the solution, okay, at any position we assign the initial condition. Then we will have this UNP1, I mean here UN plus 1, okay, is just equal to U. So we will perform iterations. We have n from 1 until 10, okay, and from 1 until 10. So what we have? We calculate the new values of U. So here we are iterating through time, okay. So this is the this is space, okay. So this is the time marching, okay. So here is time marching, the outer loop, and the inner loop here is the space, okay. space margin. Okay. So for n is equal to 1 until 10, we calculate the solution at any step. So for n is equal 1, what we do, we iterate through x is equal to 0.1, x is equal to 0.2, all the way until x is equal to 0.9. So this is just simple implementation of the finite difference scheme. We have, this is just simply un plus 1 at time I is equal to u I n minus the v delta t divided by delta x times u I n minus u I n minus n and n minus 1. Okay, then we have a vector t. We just created a vector t is equal to t plus delta t. Yeah, we just reassign, and then we update the step. So we start now with the actual implementation of the finite difference solution to the advection equation. I'm going to create a new file. I will call this file advection. Then we start first with the definition of the variables. So we start with the number of nodes, -1, this will be n, and then we go to the space boundaries. So this will be x min is equal to 0 and x max is equal to 1. Then we go to the space step length, and this will be dx is equal to the difference x max minus x min divided by the number of nodes -1. Then the time step length, this will be delta t, that is equal to 0.05. Then we have the speed at which the concentration of the pollutant or the substance is moving along the space domain. So we said we will set it to 1. Then after that we define the constant c. So c is equal, we said, is v times delta t over delta x. Then we will start the set time vector. So we put t here is equal to 0. Then we will calculate the node the positions. So this will be along this vector from x min, it goes by dx until x max. So this actually creates a vector like this, 0, 0.1, 0.2, and so on until 1.0. Okay, so here we have 0.9 and so on. Okay, now we calculate the initial conditions. Okay, so the initial conditions, they give me u0 is equal to exponential minus 100 times x minus 0.4 squared. Then what we will do here, we will assign, we will initialize the solution vector, the solution, or the approximate solution, okay, the approximate solution vector, and this is u. So we initialize, we can put it 0, but we will start, of course, with u0 directly because that's the initial condition. Now I'm going to start the solution here, start the solution. before that, what we do, I'm going to put un plus 1 is equal to u. I'm going to use this. Later you will see why it is important to have this line of code. So we will start the time marching, okay, time marching scheme or loop or whatever. Now we will perform 10 iterations of the finite difference scheme. So from t is equal to 0 until t is equal to 0.5 seconds. Okay, so put here, we open the loop for n is equal to 1 until 10. Okay, so this is the time, okay, loop. And just put here, and then we start here, okay. Then what we do, we calculate the new values of u, the approximate solution. Okay, so we will loop over, okay, so loop over the space domain, okay, we loop over the space domain. So what we have here, put for I is equal to 2 until n. So we just write un plus 1 of I is equal to what? ui minus c times the difference ui minus 1. And if you see here, if you pay attention, we started from 2 until n. We started I from 2 until n, because here we will have I minus 1. So 2 minus 1, I mean the minimum one, I is equal to 2. This term will be u of 1. You know, Matlab doesn't start the indexation, doesn't start from 0 like C and C++. They start from 1, so we should have the minimum here is 1. So in this case, it has to start from 2. Okay, good. Now we can update now the time. So we have t is equal to t plus dt, and we will update also the approximate solution u. So we have u is equal to unp plus 1. So you see why we call the unp plus 1, because we will need this. Okay, we will need to update, use it to as an intermediate to update u. So u gets updated here, okay, at this stage. Once it is updated at this stage, we can use it here. Okay, we can use it here, okay, to calculate what? The new un plus 1. Okay, now this is done, and we can plot the solution at any time. We can plot the solution at any time. So just run it and see what we will get. Here we have, just to be careful here, that must be, you see this dot, I added this dot, is very important because you're dealing with the square of a vector. You know, x is a vector, and in Matlab you cannot just put a vector square, you have to put here the dot, so that like this, you put like this. For example, you have a vector x, you want to square each term of the vector, you have to put like this. This means that it is the this broadcasting, it's called broadcasting. So each member, it means each member of that vector will be squared, okay, will be squared. This is very important, okay. Now what I'm going to do here, we can execute the file, then you can see, you can execute this. Okay, I executed. Okay, so if I put u, then I put here the last time step is 0.5, of course, and we can put u, the solution. So the solution is this. Okay, so at t, here we have at x is equal to 0, at x is equal to 0.1, 0.2, 0.3, 4, 5, 6, and 7, 8, 9, and at 1. Okay. Now, what I want to do, I want to plot the state of the of the solution at every time step. So what I'm going to do here, I'll just go ahead and come here, then we plot, okay? Plot the results, okay? Then what I'm going to do, I'm going to plot x. This x is the vector of the nodal positions against u. So every time step, every time step, we will get this solution. We capture this solution, we plot it. Then hold on. Then what we do, we don't need to pause, okay? So hold on. Then we can see all the solution steps. So I execute. Okay. So this is the solution. So as you can see here, the solution actually, what happens? It moves from the initial solution moves like from the left to the right, but here is the number of this one, number n. So let's put here, let's say 50, and we see what happens. Okay, you can also invoke this solution. Okay, so what happened? You see what happened? I increased the number of discretizations, space discretizations, but I lost the stability of the solution. So 50, it is probably too much that caused the CFA condition to be violated. So let's decrease the number of n, not 50, let's put it just 25. Run the it's there is still numerical instability. So let me just delete the figure, close the figure, then probably put n is equal to 20, then increase the number of decrease the number this one, the time step length. Run. Okay, it's much more better, but still there is a dissipation. There is dissipation. Okay, there is dissipation. On Matlab, the solution was dissipative because the amplitude gets reduced every time we move in, we march. Every time we march to in time and in space. So as you go to the right, okay, we go from the lower boundary up to the upper boundary, the magnitude reduces, whereas the correct solution should move with the same amplitude at all times. So if the initial condition is like this, so we expect the solution to follow exactly the same shape as it moves in time, okay, as it moves in time. And so on. So you see here the first one is like this. The first one is like this, then the second time 0.05 is like this, then it gets reduced as it goes to the right, then it gets reduced every time. So you can see here, this is not, it is a stable solution, but it is not accurate, okay, due to the numerical dissipation. This is called what? Due to numerical dissipation. Okay.